Okay, sir. A very warm good morning to one and all present in this gathering. Today, we have gathered here on the ninth lecture day of Saviezza, the annual Stephanian Erudite series organized by Department of Mathematics and Statistics of St. Stephen's College, Uzhavoor. यथा शिगमयूराणां नागानां मणयो तथा तद्वद् वेदाङ्गशास्त्राणां गणितं मूर्धनिस्थितम्. This Sanskrit verse, if translated, gives the meaning as a beautiful feather on the head of a peacock, as the diamond on the head of a snake, mathematics shines on the top of all Shastras. This sloga gives the importance of mathematics among various sciences. Very often, it is referred to as the queen of all sciences. At the same time, mathematics have applications in all scientific studies. In that sense, it is serving all sciences. In fact, not only in science, but also in all other subjects. Yes, friends, today we are indeed blessed to have our resource person, Dr. Gopikrishnan CR, Post-doctoral research fellow, IIT Mumbai, who is going to conduct a talk on the topic finite element method in one dimension. A day without prayer is a day without blessing, and a life without prayer is a life without power. It is a mark of our undying tradition to invoke the Almighty at the beginning of an important event. So now, I call upon Ms. Aishwarya Surendran, second year BSc Maths student, for the prayer song.
ഞങ്ങൾ നമിച്ചിടാം ഞങ്ങൾ സ്തുതിച്ചിടാം ലോകാധിനായക ദൈവമേ ഞങ്ങൾ നമിച്ചിടാം ഞങ്ങൾ സ്തുതിച്ചിടാം ലോകാധിനായക ദൈവമേ ആലോലമാനസരായും ഞങ്ങളെ കാത്തരുളിടണേ നായക ആലോലമാനസരാകിലും ഞങ്ങളെ കാത്തരുളിടണേ നായക നാടിന്നു നന്മയും ശാന്തിയും കൈവരാൻ ഞങ്ങളിൽ ഐക്യം വളർത്തണേ നാടിന്നു നന്മയും ശാന്തിയും കൈവരാൻ ഞങ്ങളിൽ ഐക്യം വളർത്തണേ ഞങ്ങൾ നമിച്ചിടാം ഞങ്ങൾ സ്തുതിച്ചിടാം ലോകാധിനായക ദൈവമേ.
Thank you, Aishwarya. We all feel very blessed indeed. Now, I would like to call upon Ms. Jayalakshmi G. Nair, third year BSc Maths student, to formally welcome the gathering.
जयलक्ष्मी क्या काम हो? जयलक्ष्मी क्या नहीं खेर में? जयलक्ष्मी क्या नहीं खेर में? ज्योतिका
Okay, sir. Next, I would like to welcome Lieutenant J. Kurian, sir, HOD of Mathematics and Statistics Department, to chair the session. Please, sir.
Respected our chief guest, Dr. Gopikrishnan, respected principal, Professor Lalli Kesarek, respected teachers, or Bersar Father Jins Nilligatil, and other teachers, research scholars, and my dear students. Mathematics often looks like a collection of symbols, but mathematics is not the symbols on the page, but what those symbols mean. And it doesn't matter what country you are from or what language you speak. If you are trained in mathematics, you will also understand what those symbols mean. So it is a universal language. It rises above words. In fact, it is quite possible that mathematics will be the common link between ourselves and any aliens we may one day meet again. Today, we are the 10th day of our webinar series, Saviezza. And I am extremely happy to welcome you all in this gathering. First of all, I would like to welcome our chief guest, Dr. Gopikrishnan, in this gathering. As you all know, he is a postdoctoral research fellow at IIT Mumbai. And also, he is a native of Kidangur, which is near our college. And after schooling at Kidangur, he joined at ISER Trivandrum for integrated MSc program in mathematics and completed the same with a silver medal for the best academic performance and the highest CGPA in 2015. And also, he cleared the CSIR Junior Research Fellowship exam 3 times successively. And also, he cleared the GATE exam. And after that, he joined IIT Mumbai Monash PhD program, and which is a very good program. A very few number of people from Kerala already joined it, and he completed his PhD in 2021 on the topic numerical methods for free boundary problems in 3 dimensions with applications in biology under the guidance of the famous Professor Jerome Donahue and Professor Jennifer A. Flagg and Professor Neela Nandraj. And now he is working as a postdoctoral research fellow at IIT Mumbai. His research interests span from mathematical modeling of different physical problems with a special interest on problems from life sciences. His PhD topic is actually research in cancer diagnosis, and also he used theoretical and numerical analysis of systems that contain all pairs of hyperbolic or elliptic or parabolic partial differential equations. Usually, such systems originate from modeling of biological phenomena using multiphase fluid flows and multiphase mixture theory, and appropriate combinations of finite volume and finite element finite difference methods are used to design numerical schemes. In his research, he used various compactness techniques to carry out convergence analysis of numerical schemes and establish the existence of weak solutions to tightly coupled solutions. He has already 8 international publications in his credit and an expert in mathematical packages like Mathematica, MATLAB, etc. He gave talks in prestigious institutions like Oxford University, Brunel University, London, Newcastle University, Australia, Monash University, and University of Melbourne, and also IIT Mumbai. He believed that a successful and satisfying career in mathematics is the right blend of two complementary activities. One is creation of knowledge by actively participating in research, and second, creation of human resource by teaching skills and methods learned through research. I will not go into the detail of the importance of mathematics research because the resource person, Dr. Gopikrishnan, will tell you the outline later. And on behalf of all the teaching faculty and students of our college, I extremely welcome Dr. Gopikrishnan to our college. Welcome, Gopi sir.
Thank you, Jay sir.
Secondly, I welcome our college principal, Lalli Kesariyak, and our bursar, Father Jins Nallikadal, and all the faculty members, and all the research scholars and teachers from various colleges, and all the student participants to this occasion. I once again welcome all the dignitaries who gathered here. Okay, thank you. Over to Gopi sir.
Thank you, Jay sir. It is a very nice introduction. Let me share my screen. Somebody should tell if you can see it. So is it visible?
Yes, visible.
Thank you, Jay sir. Of course, St. Stephen's is very much dear to me for reasons that belongs to many facets of life. I started my career in 2015, May 30, I guess, when I joined BCM College Uruvur, Kottayam. And I believe the first talk I delivered ever in my life was at St. Stephen's Uruvur. So because of that main reason, it's always one of the dearest college, and of course, Prof. Jay sir and his wife are two lovely, dearest persons in my life who have supported me through many ways. So once again, thank you, and I'm always glad to take up a commitment demanded by Jay sir. So without further ado, let me start the talk. Finite element method it's an unfamiliar term to many of fellow attendees here. Some may be very familiar and some may be expert. So I was designed this lecture specifically for the BSc and bachelor and master students in mathematics, usually who follow the syllabus designed by state universities of Kerala, which is still, I should say, it's pretty archaic, and so the framework of finite element method usually starts from the Sobolev spaces and analysis of partial differential equations in Hilbert spaces. But apart from a functional analysis course, there is no commendable emphasis on advanced mathematics being given to the courses taught in our university. So this may not be strictly accessible to many attendees. However, I will try to make it as simple as possible, as easy as possible, and we will go very slowly. I have not hurry at all, and we are also not in a mood to finish the entire finite element method in 1 hour, which is also not possible. Usually, this is something that we teach over 2 or 3 weeks. So if Students or any attendees have any questions, don't hesitate. Please stop me in between. My plan is just to give a motivation of, so let us write here what is our plan. The plan is, we want to motivate why FEM or finite element method is needed, so why it is necessary. Okay, and then we will show an application, a very simple application using a one-dimensional problem. So let us try to illustrate an application using a 1D problem. And if time permits, I'm not sure whether we can finish 2 entirely. But if time permits, I will show you some examples in 2 dimensions and possibly 3D. So this is question. I am not sure whether we are able to do this, but so the emphasis will be mostly on the motivation. So this we have to finish anyhow, and some part of 2. So 3 we will follow if we have enough time. Okay, so well, most of you, I think some of you, or at least 60% of the attendees are familiar with what are finite difference methods, which is very classical. A finite difference method is a very simple numerical scheme that is used to approximate partial differential equations. Often when we try to solve, so differential equations, in particular partial differential equations or ordinary differential equations, model certain physical phenomena. For instance, if you take heat equation models. So let's take heat equation. Heat equation models the propagation of heat across, for example, a 2-dimensional lamina. Suppose you put a candle here and flame it. So what happens is this will be the hot end and this will be the cold end. And what will happen is the heat will propagate from this side to this side. Now the question is, given the initial temperature of this rod and what is this source, say example F, can you predict the temperature distribution at each point in this lamina after a time t? Okay, so in mathematical terms, we will write this as a PDE, which is the well-celebrated heat equation. I presume most of you know this. At least MSc students should know. It will be something like delta U minus gradient of lambda grad U equal to F. The lambda is the thermal conductivity of this rod. So lambda is the thermal conductivity. And U is the U of xt is the temperature at space point x and t. Okay. Now this is a particular example of one physical phenomena, and we have a PD, and this will be supplemented by some initial condition and some boundary conditions. So I think this is familiar to most of the activities. Now we can solve this problem analytically, or in a course language, we can solve it using a pen and paper, which means that we can find a closed form expression for U. And when we substitute that expression in this equation, it will satisfy this equation. That means the right-hand side will be equal to the left-hand side. Now, the use of PDE or the use of modeling is to understand what is happening in nature. So when we model complicated natural phenomena, it may be difficult, or in usual cases, in practical cases, it's often very difficult to predict what U is, which means that we may not be able to derive a closed form an analytical expression for U. Okay, for instance, the problems I am working on that related to mathematical biology, it involves a coupled system of parabolic, elliptic, and hyperbolic PDE. Okay, and it's a system. It's coupled. The variables are coupled with each other, and it comes with many initial conditions and boundary conditions. And if we try to find a solution for that, it will take decades, if at least the time permits, or it can take centuries. Okay, but we don't have that much time remaining to it. So what we need practically is an approximation to the exact solution. What we need is approximation to the exact solution, which is the fundamental motivation of all numerical methods, whether it is finite difference, finite element, or finite volume. The numerical scheme approximates an exact expression, a solution to a PDE or an ODE. Now, is there any questions so far? Can I continue? Yeah, somehow the voice from Jesa side is not very clearly audible. So I believe I can continue. If you have any question, one thing you can do is you can put it in the chat box and I will reply that. Okay, so the finite, so the numerical methods are of different types. It's called finite difference, finite element, and finite volume. Now, finite difference methods are the first classical methods, one of the classical methods. So I think my voice is very low. Let me speak a little aloud so that it will be audible. Give me some feedback. Is it audible now?
Yes, sir, it's audible.
Okay. Yeah, I have a common complaint from all panelists that I have a very timid voice. So sorry for that. Apologies. I will try to speak aloud. Now, numerical methods, one of the classical numerical method is finite difference method. And finite difference method, what we do is we take a differential operator and try to approximate it using a difference equation. And this difference equation we try to solve iteratively, which will give solution, approximate solution to the exact one. But the issue with finite difference method is we always need a lamina, a domain similar to that has some kind of Cartesian geometry. Okay? For instance, if you're going to solve a two-dimensional problem using a finite difference, we always need a lamina like this so that we can discretize the whole domain into rectangular cells. Okay, and the intersection of these lines will be our nodes. Okay, so instead of finding the derivative at every point, we will try to find the derivatives at these nodes, and using that we will derive an approximate equation, a difference equation, and we solve this difference equation, and that difference equation will give an approximate solution CUH. Okay, now can anybody tell what is the issue with this method? Usually in talks, it's not very advisable to ask questions to the participants. So maybe I will continue myself. The issue is, suppose you have you want to find the temperature across the points in an aeroplane lamina, in an aerofoil. Okay, for example, if you have some shape like this, how do you discretize this? Okay, if we do like something like this, we will miss some points here. See. Some points will be outside, some points will be inside, and it will be very difficult to design a finite difference method on laminas that does not admit a Cartesian geometry, which is one of the importance of finite element method. Thank you. So, so the fundamental motivation of finite element method is how can we design a numerical scheme on a domain that does not admit particular Cartesian geometries. Okay, for example, we can have a circle, we can have an aerofoil, Okay, finite element methods itself were discovered by engineers, and it was applied in aerodynamical engineering, mechanical engineering, or civil engineering to find structural integrity of civil engineering structures, or the temperature distribution across the lamina of an aeroplane, and to solve such and such problems. Now, keep in mind that none of these structures, okay, for example, if you take a building or if you take an aeroplane foil, it does not have Cartesian geometry. So you need a method that can allow us to solve it using that does not demand for Cartesian geometries. Okay. Now let's start with the main. So this is the importance of or motivation of finite element method. Okay. Now let's understand what's happening here, or what is the physical motivation. Suppose we consider the following 2-point boundary value problem. So let's take a one-dimensional example. Somebody should let me know the time when I want to stop. Okay. So for example, consider something like minus u double dash of x equal to f of x. So this is a ODE. It's a 2-point boundary value problem augmented with 2 boundary conditions at x equal to 0 and x equal to 1. And the problem is defined on the interval 0 less than x less than 1. Now, all of you know how to solve this equation. What you have to do, you have to integrate it 2 times. Because this is a very simple equation. You integrate it 1 time from 0 to x. So the first integration will be something like, so when you solve, I think the u of x will be integral 0 to x, integral 0 to s, f of r dr ds with a negative sign. Okay, you perform a double integration, and then we will get what's the solution. So in this case, we know the exact solution. Now suppose that we don't know what's the exact solution. How we are going to compute an approximate solution? In this case, it is sure that okay, there exists a solution, and let's call that solution by the name D. Okay, so D is the exact solution to this boundary value problem, which we can compute. So we can establish also analytically using Picard's iteration method, and that okay, this has a solution, and the solution is what we have computed. Okay. Now, what we can show is this is also a solution to a minimization problem and a variational problem. So at this point, somebody should ask me a question: what is a variational problem? Somehow my audio settings has itself switched on. So yeah. So what is a variational problem? So this we will explain in a few moments. Okay. So what I was saying is the solution D happens to be a solution of a minimization problem. What minimization problem? That I will explain later. And a variational problem. And a variational problem. So what are these guys that we have to explore? Okay. So before that, let's introduce a few notations. So the inner product is defined by inner product UV is just L2 integral 0 to 1 u of x vx dx. Okay, and we define a space B by B is the collection of all functions V on 0, 1 such that A is continuous and B the derivative B dash is piecewise continuous and bounded on 0, 1. So we don't say that the derivative has to be continuous everywhere. It just has to be piecewise continuous. For instance, functions like this are allowed. So let's take 0, 1, and it's possible to have this may be a possible graph of V dash. Okay. So look at here. So we don't say that V dash has to be continuous. V dash can be discontinuous also, but it has to be piecewise continuous. Also, we need a V of 1 and V of V of 1 and V of 0 has to be 0. Now we define a linear functional from V to R, the space V to R by f of V equal to half V dash minus Fv. Okay. So if you know some physics, you should get already some hint where we are heading to. Okay, we all always know what is kinetic energy. Kinetic energy is half mv square, and v is always du by dx. Sorry, du by dt. The displacement in time, the time derivative. But otherwise, the kinetic energy will be the gradient square. So we can be also du by dx when we solve this spatial problem. So any questions so far now? That means either everybody understood everything or something is fishy. So let me continue anyhow. So we defined an inner product, and we defined a space, and we defined a linear functional from V to R, which is equal to f of v given by half v dash minus inner product f. So this is simply fv is half integral 0 to 1 v dash square dx minus integral 0 to 1 dx. So that's a shorthand notation for this. Okay. Now, what's the minimization problem? So we are trying to minimize something. Okay. Now, if you look at here, as I said, this f of v denotes some kind of energy. Some kind of energy. What does that mean? If you look here, this guy here, 0 to 1 v dash square, this is the potential energy or the elastic potential stored in a material. And f is the load function. So this is the potential energy due to the load function. Okay, imagine that you are pulling a spring down with a load f. Okay, so the f will give a potential energy, and then there will be a stored elastic energy in the spring itself. Okay, so this first term denotes the elastic energy in the spring, and the second term denotes the potential energy due to the load. So the sum is the total energy of the spring system, or total energy of any system, any elastic system we are trying to model. So basically, we know from physics that systems tend to attain the state where it achieves the minimum energy. Always systems try to achieve the state of minimum energy, right? So what we are trying to solve is find a displacement u such that the total energy is minimized. Okay, arc minimum represent the minimum argument on which this energy is minimized. Okay, or we are seeking that particular displacement u at which the system is least perturbed, or the system has the least energy. Okay, now what's a variational problem? Variational problem seek a u belongs to v such that it should true that 0 to 1 u dash v dash dx equal to integral 0 to 1 f v dx for all v in p. So instead of trying to solve the whole PD itself, we are trying to solve an integral equation. And what is the demand? The demand is to find a u such that this integral equation in green color star holds true for every v. If you take a particular v from the space v, what was v? V was the set of all continuous functions, and its derivative has to be piecewise continuous. If we say take one particular v, take its derivative, multiply with u dash, and integrate on 0 to 1, it should be same as 0 to 1 f dx. So this is called a variational problem. So now we have three problems. Okay, we have a variational solution, we have a minimization solution, and we have an exact solution. How these are related? Questions? So I had a faculty named Matai. He was teaching me in some entrance institute. This guy has a very peculiar character, so he will always prompt to ask questions, And the demand from the faculty is that he will not continue the class unless at least one student asks a question. So I should ask him that. People should give me some feedback. Any questions from the motivation or the mathematics? I guess not, so let's continue. Yeah, so what I was trying to explain is how these three solutions, the minimization solution, the variational solution, and the exact solution are related. Okay? So we have two important results. Let's take theorem 2.1. It states that a solution of 1.1, which means a solution D, is also a variational solution. So if you take an exact solution, it will be a variational solution. How? So it's very easy to follow. Let's take the PD. So what's the PD? We have minus u double dash is equal to F. What you do is take a V. So let's take V in V. Okay. And let's multiply and integrate on 1. So integral 0 to 1 u double dash V dx equal to integral F V dx. Integrate on both sides. Now, question, how many of you are familiar with integration by parts? In Zoom, usually you can conduct some kind of poll. I'm not sure whether we are able to do that here. I don't know, maybe the host can conduct some kind of poll asking the participants to know if something is familiar or not, that I can explain.
Hello, Gopi sir.
Yes, sir. Parna sir.
BSc പിള്ളേർ ആയതുകൊണ്ടേ അവർക്ക് ചിലപ്പോ ഒരു ചോദിക്കാനുള്ള ഒരു മടി കൊണ്ടായിരിക്കും.
അത് കുഴപ്പമില്ല, ചോദിച്ചോളൂ. Okay, integration by parts means, let me continue. Integration by parts means if you have the formula is, we will write in a different color. So this is for one-dimensional domains. If integral 0 to 1 double dash dx, what we do is that shift one derivative to the function. So this will be integral 0 to 1 u dash v dash dx plus u dash v evaluated between x equal to 0 and x equal to 1. So this is a boundary term and this is a mass term. So when you apply this formula to this equation, what you will get? You will get this formula. Okay, so you will get u dash v dash dx minus v of 1 u dash of 1 minus v of 0 u dash of 0 equal to integral 0 to 1 f v dx. Okay, now because of the boundary condition, this term will vanish and you will only have integral 0 to 1 u dash v dash dx. Okay, because we had a boundary condition for the PD which states that u of 0 0 and u of 1 equal to 0. So you will end up in this PD. So this integral equation, which means that u dash is a variational solution. Okay, it's like we are varying p, that's why it's called variational solution. So every exact solution is a variational solution. Now, the second result is the variational problem and the minimization problem have the same solution. In other words, the variational problem and the minimization problem are reformulations of the same physical phenomenon. Okay, so how do you prove this? Let's start with a variational solution and we will show that. So this is from variational solution is a minimization solution. How do we show this? So let's start with a variational solution u, which means that u dash v dash has to be a v for every v in v. Okay, so let's choose an arbitrary v in v. Okay, and we will define w as the difference between v and u. So we have u, this is a space v, and we have u here, which is the solution to our problem. It's the variation solution. and here we have b, which is an arbitrary function. So we are taking this difference and we call that by w. Okay, so let's compute what is f of v. What was f? F is a linear function, the energy functional, and f of v will be v is w plus u, w plus v. Sorry, this is w plus u. Okay, what will be that? That is half w dash u dash plus w dash u dash minus f w plus u. Now expand this inner product. How many of you are familiar with inner product? I was saying inner product left and right, and I haven't asked the question how many of you are familiar with inner products.
Inner product നമ്മുടെ MG യൂണിവേഴ്സിറ്റിയില് MSc ആണ് ഇൻട്രൊഡ്യൂസ് ചെയ്യോളെ. BSc കുട്ടികള് 6th സെമസ്റ്ററിലാണ് കുറച്ച് ഫെമിലിയർ ആവുള്ളൂ.
Okay, so here is an assignment for you. Go to the library and find what is an inner product. So you understand what are vector spaces and what is inner product. So these are topics that you can learn yourself. You don't need a really a faculty to do this. It's very easy topics in math, functional analysis. So try to learn this. Loosely speaking, an inner product is you take a function space. For example, you must know dot product, right? Vectors you must know. So inner product is a generalization of vector dot product basically. So you have two vectors u and v, and you take u dot v. So instead of that, you construct an abstract dot product, something like uv. Okay. So instead of defining that as u dot v, you define that as some kind of integral. Okay. Or you can define that as u of 0, v of 0. You can define in different ways. So basically, it should be linear in both of its arguments. What is linearity? Which means that if you add u plus w, so I can explain with this example itself. So you see here, what I can do is that I can write this as w dash plus w dash u dash w dash plus w dash u dash u dash. Okay, basically, if we have a, b plus c, it should be to ab, a bit off the topic. Yeah. So what happened here is we can split it like this, and we already know that u is a variational solution. So this term, this difference will be 0. And what we have is half w dash, which is here, and half u dash minus f of u is the kinetic energy. So this we can plug in here. So this f of v is f of u plus half w dash. Now inner product, when you have the same argument, it has to be always positive. Okay, so that's the property of the inner product, which means that this guy is always greater than f of u, because it's f of u plus a positive quantity, which means that this is greater than f of u. Which means that f of v is greater than or equal to f of u for every v, which means that u is a minimization problem solution. Okay, so which means that if you start with a variational solution, that happens to be a solution of the minimization problem. Conversely, let's start with the solution of a minimization problem. Okay, which means that let's take u as a solution of the minimization problem, and let's take a v in v, okay, and real number epsilon. And let's construct another function u plus epsilon. Since u is a minimization solution, it holds that f of u will be the energy at u will be always less than the energy at f of u plus epsilon. Okay, so call this guy f of u plus epsilon v as g of epsilon. Okay, so this is g of epsilon is equal to f of u plus epsilon v, and you can apply the definition of the energy here. So this is half u dash epsilon v dash plus u dash epsilon v dash minus f u plus epsilon v. Again, apply the linearity of this guy, the whatever it is, the inner product. We can expand this in some form. Now, what we know is that g of epsilon is least when epsilon equals 0. Why? Because the f of u will be the smallest quantity, which means that g as a function attains minimum at epsilon equals 0. So we can compute what's the derivative. So which means that g dash of 0 has to be 0 because of the test condition, first derivative test condition, and we can find what is g dash of 0. Now g dash of 0 we can find this in first principles, and it happens to be equal to, you perform this computation is very easy. It will be u dash v dash minus f of v equal to 0, which equal minus f of v. Since g dash of 0 equal to 0, the whole equality sandwiches, which means that u dash v dash equal to Fe, which means that the function is a minimization solution. It's a variational solution. So every minimization solution is a variational solution, which means that now minimization problem has physical sense. It means that you are trying to find that displacement at which the system attains the least energy. The variational solution also finds that. Okay, now this we are trying to, in finite element method, what we are trying to approximate is this variational solution. In other words, what we are trying to approximate is that displacement which minimizes the total energy of the system. Okay, so finite element method is very natural in the sense that it tries to approximate the natural state of the system. That means the displacement that minimizes the total energy. Is that clear? At least the philosophy is clear to students. Confused between chat and participant button. Is it clear?
ഓക്കെ സാർ, നിങ്ങൾ പാർട്ടിസിപ്പൻസിന് എന്തെങ്കിലും സംശയം ചോദിക്കാൻ ബുദ്ധിമുട്ടുണ്ടെങ്കിൽ ചാറ്റ് ബോക്സിൽ ടൈപ്പ് ചെയ്താൽ മതി കേട്ടോ. ഈ ആർക്കെങ്കിലും ഇംഗ്ലീഷ് ചോദിക്കാൻ ബുദ്ധിമുട്ടാണെങ്കിൽ
മലയാളത്തിൽ ചോദിച്ചോളൂ, ബുദ്ധിമുട്ടൊന്നുമില്ല. Anything if you want to understand from the process what we have discussed. In a product അതല്ലെങ്കിൽ എന്താണ് minimization?
പ്രിയപ്പെട്ട വിദ്യാർത്ഥികളെ, നിങ്ങൾ സംശയം എല്ലായ്പ്പോഴും കിട്ടിക്കൊള്ളണമെന്ന് നിർബന്ധമില്ല. അപ്പൊ അതുകൊണ്ട് നിങ്ങൾ കിട്ടിയ അവസരം പരമാവധി ഉപയോഗിക്കുക. നിങ്ങൾക്ക് അറിയാവുന്ന സംശയങ്ങൾ നല്ല നാടൻ മലയാളത്തിൽ ചോദിച്ചാലും മതി. ഇപ്പൊ സാറ് പറയുന്ന ടോപ്പിക് ആണെന്ന് നിർബന്ധമില്ല. അതുമായിട്ട് ബന്ധപ്പെട്ട വേറെ ഏതെങ്കിലും ചോദിച്ചാലും സാർ അതിന് മറുപടി പറയുന്നതായിരിക്കും.
നിങ്ങൾക്ക് മനസ്സിലൊരു സംശയം വന്നത് ഫയർ ചെയ്യുക. ഓക്കെ, യൂഷ്വലി masters അല്ലെങ്കിൽ regular postgraduate അല്ലെങ്കിൽ undergraduate students in the mistake, they will try to solve it their own. Okay, I will tell you a story. Maybe you haven't heard this, you have heard this, or you haven't heard this, I don't know. So there was this happened, I think in Rutgers or something, Rutgers University maybe. So there was this faculty, so he has written some open problems in his board. So which means problems that hasn't solved. I am not sure, there may be some technical incorrectness because I am not sure. This was taught to me by one of my faculties. So, apologies for the technical mistakes, but the summary of the story is this. So the faculty writes some open questions in the board. Open question, there was a latecomer to the class. താമസിച്ചാണ് വന്നത്. അപ്പോൾ ഇദ്ദേഹം കണ്ടത് ബോർഡിലെ ക്വസ്റ്റ്യൻസ് എഴുതിയിട്ടിരിക്കുന്നു. അപ്പോൾ ഇദ്ദേഹം ഓർത്തത് അസൈൻമെന്റ് ക്വസ്റ്റ്യൻസ് ആയി. In fact, centuries not solve problems. So this guy thought that it was assignment problems. He was already late in the class. So what this guy did is he went back to his hostel or apartment and he solved, there were like 5 questions. He solved 3 of the questions, but he missed 2 of them. 2 of them he couldn't solve. And the next day this guy went to his faculty and said that, okay sir, I am very late to submit the assignment. I could solve with it. The faculty was like enthralled. Like this was something, it wasn't solved for like centuries, and this guy did not know it were open questions. And he solved 3 open questions in like 2 weeks. So the point of the story is you ask questions. So something might happen. Okay, sometimes it may end up in a very good result. Okay? One of my faculty in ISR used to solve, there are no stupid questions, there are only stupid answers. Okay, so every questions are valid. There is some kind of explanation for it. So don't hesitate, ask questions if you have, or put the questions, whether it is in the native tongue or English, I don't care. Okay. So what? Let me continue and at least try to finish the talk. So what we proved is we have the exact solution, variation solution, and minimization problem. So variation solution and minimization problem are the same thing. And if we have the direct solution, exact solution, that happens to be a variation solution. Now, if we have a variation solution and the function is continuous, then that will be an exact solution also. Okay? So this is a chain of indication. So the advantage of finite element method is it is trying to approximate the variation solution. Okay? Now, how do we do it practically? So our test space V was all functions. So V was functions such that U is continuous and U dash is piecewise continuous. Okay, so let's try to approximate the U using the easiest piecewise continuous function we know. Okay, we can try to approximate functions using polynomials. Okay, that is the starting point of finite. Suppose we have a function like this. Okay, on 0 to 1. Okay. Instead of trying this function, trying to find this function, let's write nodes here. So I'm going to discretize 0 to 1 into discrete points. So this is h, 2h, 3h, 4h, 5h, and 6h equal to 1. So h is basically 1 by 6. Okay. 1, 2, 3, 4, 5, 6, 7. So maybe 1 by 7. Okay. So what we're trying to do is we're trying to approximate this one using linear polynomials. We don't need the exact curve, we just need an approximation. Okay, so for example, I can draw a little bit bigger diagram so you know what happened. Instead of finding this, apologies, what I'm drawing are straight lines. Okay, we're trying to approximate it using linear polynomials. Okay, so this is a starting point. Now, how do we do this? How do we do this? That's a question. So, what is the problem that you have to solve? You have to solve u dash v dash dx equal to integral 0 to 1 f v dx. Okay. Now, we don't test for every function v. We test for some particular choices of functions, which are called basis functions. Okay. We will create a discrete space. Okay, that consists of functions like this. So I have my 1, 2, 3, 4, 5, 6. I can't draw a lot, so please forgive me. So let's take this one. So my first basis function will be like this. Okay, it has a piecewise continuous derivative, so this belongs to V. So let me call this x0. Okay, second function will be like this. And third function will be like this. Sorry. So you see, it's 1 at one node and linear on the intervals adjacent to it and 0 at all other points. So this is my phi 2. And this will be my last one. So we take v is equal to phi 0 and find what is this. What does the equation mean? We take v equal to phi 1 up to v equal to phi 0. So the first one will be integral 0 to 1 u dash phi 0 dash dx equal to integral 0 to 1 f phi 0 dx. Okay, and this will give me a difference equation. Why? You see, phi 0 is 0 everywhere else apart in the first interval. So this implies integral 0 to h u dash phi 0 dash dx equal to integral 0 to 1 or 0 to h f phi 0 dx. The logic clear? Right. Now, let's take, so I should have written a UH dash. This will not make any sense. Now, what is phi 0 dash? Phi 0 dash is basically slope of phi 0. Okay, and this we can compute very easily. This is 0, h, and this is 1. So what will be this, the slope? This will be, so the derivative of this function, so it will be 1 by h with a, is it 1 by h? So if you take tan theta, this is 1 by h, opposite side by adjacent side, but the slope is on the other side, so this is negative 1 by h. So this is implies integral 0 to h 1 by h u dash dx equal to integral 0 to h f phi 0 dx, which implies 1 by h u of 1 minus u of h minus u of 0 equal to integral 0 to h f phi 0 dx, which implies, so let's call this as u of h is u1 and u of 0 as u0. So we'll get the equation 1 by h u1 minus u0 equal to integral 0 to h f by 0 dx. Likewise, we can solve for other equations. Okay, so what we will get is, so let me write the convention. So the value of the function at approximate value of the function 0 is u0, u1 up to u7. Okay, so we will get a system of equation, a matrix system to compute u1. So it will be look like, so let me write here, we'll get a sparse system. So this will be minus 1, 1, 0, 0, 0, 0, and the next it will be 1 minus 1, 1, 0, 0, 0, 0, 0, 1 minus 1, 1, 0, 0, 0. Likewise, I will get here minus 1, 1. Sorry. So basically, you have to integrate each equation on the basis function and get a system. So I will get 1 here with 1 by h, which is equal to integral 0 to h f phi 0 dx up to integral, what will be the last 1 minus h f phi 7 dx. Okay, so this is of the form AU equal to B, where B is this lower term and A is matrix. So this we can solve using A inverse B to find what is U. Okay, so this U will be, actually I should write UH. So this UH will be a piecewise linear approximation of the exact solution. Okay, so this is how finite element method work. Okay, we try to approximate the function using piecewise linear polynomials. So this is called, in finite element language, this is called conforming P1 FEM. P1 means we are trying to approximate use first order polynomials. We can do P2 also. Then it will be called conforming P2 FEM. Okay, so this is the fundamental philosophy or the working rule of finite element methods. Okay, now this is for one-dimensional problems. Now you can do this also for 2D problems, for example, but in 2D problems, I'm not sure whether I'm right. I can write here. In 2D problems, what we do is that instead of discretizing the domain using intervals, we will discretize it using triangles. Like this. Okay, you can continue this. So triangles nicely approximate the shape. Okay, and on each of this node, we try to approximate the function. Okay, so there are many kinds of FEMs on one dimension. There are something called conforming finite elements, non-conforming finite element, which is, I think, it's 2 out of the syllabus. So just keep in your mind that this is a very broad field. It's a very, very actively research pursuing field in modern mathematics and also in engineering, and which are very interrelated one to another FEM. This is I think this is one of the latest and most applicable, most used methods nowadays. Okay, so I guess I have tried to give an impression what is FEM, how do we carry out that, and what is its motivation. So I think this is 12 o'clock now. Maybe I will stop here and I can take questions from you guys if you don't understand. So please do ask questions. I will try to clarify.
ഗോപി സാറേ,
എന്തോ
ഞാനിപ്പോ ഒരു ക്വസ്റ്റ്യൻ ചോദിക്കണേ. സാർ ഇപ്പൊ ട്രയാങ്കിൾ വെച്ചിട്ടല്ലേ അപ്രോക്സിമേറ്റ് ചെയ്തേ?
അതെ.
നമ്മൾ നോർമലി നമ്മൾ സ്ക്വയേഴ്സ് വെച്ചിട്ടല്ലേ അപ്രോക്സിമേറ്റ് ചെയ്യുന്നത് നമ്മൾ ഏരിയ കാൽക്കുലേറ്റ് ചെയ്യുമ്പോ?
അതെ, അങ്ങനെ ചെയ്യാം. ട്രയാങ്കിൾസ് ആണ് സാർ കുറച്ചുകൂടെ ഈസി ആയിട്ട് ചെയ്യാൻ പറ്റും. നമുക്ക് റെക്ടാങ്കിൾ യൂസ് ചെയ്യുന്നതിന് ഒരുപാട് ഡിഫിക്കൽട്ടീസ് ഉണ്ട്. ഭയങ്കര സ്കീം ഒരുപാട് എക്സ്പെൻസീവ്. ഫോർ എക്സാമ്പിൾ നമുക്ക് ഇങ്ങനെ ഒരു സൈഡ് ഉണ്ടെന്ന് വെച്ചു, ഒരു കോൺവെക്സ് സൈഡ് ഉള്ള ഒരു ഡൊമൈൻ ആണ് നമ്മൾ അപ്രോക്സിമേറ്റ് ചെയ്യാൻ പറ്റുന്നത്. സോ ഈ കോർണർ അപ്രോക്സിമേറ്റ് ചെയ്യണമെങ്കിൽ ഒരുപാട് സ്ക്വയർസ് വേണം, വെരി സ്മോൾ സ്ക്വയർസ് വേണം. ഓക്കെ, സോ ദാറ്റ് വിൽ മേക്ക് ദ സ്കീം വെരി ഡിഫിക്കൽട്ട് ടു പെർഫോം ഇൻ എ കമ്പ്യൂട്ടർ. ട്രയാങ്കിൾ ആണെങ്കിൽ ആ ബുദ്ധിമുട്ടില്ല. ഇത് നമുക്ക് ട്രയാങ്കിൾ മാത്രമല്ല, ട്രയാങ്കിളിന് അതിന് പകരം പല രീതിയിലുള്ള പോളിഗൺസ് ഉപയോഗിച്ച് അപ്രോക്സിമേറ്റ് ചെയ്യാം. ഓക്കെ, സോ പോളിഗൺസ് ഉപയോഗിച്ച് അപ്രോക്സിമേറ്റ് ചെയ്യുകയാണെങ്കിൽ അത് VM എന്നാണ് പറയുന്നത്, വിർച്വൽ എലമെന്റ് മെത്തേഡ്. Okay, so this is using polygons. So instead of triangles, you can use quadrilaterals or hexagons. You can use quadrilaterals or hexagons, any shape that you can tessellate a domain. So that is called VM. The thing is, you have number scheme economical icon. So the shape, the shape with a tessellate other number scheme സ്കീം കുറച്ചുകൂടെ നമുക്ക് പെട്ടെന്ന് ചെയ്യാൻ പറ്റുന്ന രീതിയിലായിരിക്കും ഡിസൈൻ ചെയ്യുന്നത്.
ഓക്കെ സാർ. അതുപോലെ രണ്ടാമത്തെ ക്വസ്റ്റ്യൻ സാറേ, നമ്മള് 1 ഡയമെൻഷനിൽ വേവ് ഇക്വേഷൻ ഒക്കെ സോൾവ് ചെയ്യാനായിട്ട് നമ്മൾ ന്യൂമറിക്കൽ മെത്തേഡ്സ് ഉപയോഗിക്കുമല്ലോ, അതേപോലെ തന്നെ ഈ ഫൈനൈറ്റ് എലമെന്റ് മെത്തേഡ് വെച്ചുകൊണ്ട് നമുക്ക് ഈ വേവ് ഇക്വേഷൻ സോൾവ് ചെയ്യാൻ വേണ്ടി പറ്റുമോ?
യെസ് സാർ, ഫൈനൈറ്റ് എലമെന്റ് മെത്തേഡ് നമുക്ക് ഏത് പ്രോബ്ലത്തിന് വേണമെങ്കിലും അപ്ലൈ ചെയ്യാം.
ഏതാണ് എക്കണോമിക്കലി കുറച്ച് നല്ല ആൻസർ തരുന്നതും സമയം കുറവെടുക്കുന്നതുമായിട്ടുള്ള
വേവ് ഇക്വേഷൻ നമുക്ക് ഇപ്പം so let's take a wave equation. So that is del TTU minus del XX v equal to say this operator should be plus I guess. ഇത് സോൾവ് ചെയ്യണമെങ്കിൽ നമുക്ക് സാധാരണ ചെയ്യുന്ന ടെമ്പറൽ ഡെറിവേറ്റീവ്, ടൈം ഡെറിവേറ്റീവ് നമ്മൾ ഫൈനൈറ്റ് ഡിഫറൻസ് വെച്ച് അപ്രോക്സിമേറ്റ് ചെയ്യും. കാരണം ടൈം ഇപ്പോഴും 1 ഡയമെൻഷനിലായിരിക്കും. Time you cannot have a time in 2 dimensions. There is nothing called 2 dimensional time. Time is 1 dimension, we can apply finite difference. Spatial derivative we can apply a finite element. So this is a combination of FD and FEM. This is called finite difference finite element method. അങ്ങനെ നമുക്ക് നമ്മുടെ പ്രോബ്ലം വരുന്ന അനുസരിച്ച് പ്രോബ്ലത്തിന്റെ സ്ട്രക്ചർ അനുസരിച്ച് നമ്മൾ 2 അതിലധികം മെത്തേഡ് ചിലപ്പോൾ കമ്പൈൻ ചെയ്യും.
ഓക്കെ സാർ.
ഹീറ്റ് ഇക്വേഷൻ സോൾവ് ചെയ്യുമ്പോഴും അങ്ങനെയാണ്. നമ്മൾ ΔTU എന്ന് പറയുന്നത് ഫൈനൈറ്റ് ഡിഫറൻസ് വെച്ച് അപ്രോക്സിമേറ്റ് ചെയ്യും. ഈ സ്പേഷ്യൽ പാർട്ട് നമ്മൾ ഫൈനൈറ്റ് എലമെന്റ് വെച്ച് അപ്രോക്സിമേറ്റ് ചെയ്യും.
പക്ഷെ ലാപ്ലേസിന് ഈ 2 ഡയമെൻഷനിൽ അപ്ലൈ ചെയ്യാൻ പറ്റുള്ളൂ ഫൈനൈറ്റ് എലമെന്റ്?
അല്ല,
ഇക്വേഷൻ 2 ഡയമെൻഷൻ ഉണ്ട്.
ലാപ്ലേഷ്യൻ 2 ഡയമെൻഷനിൽ ആവുന്നില്ല, 1 ഡയമെൻഷനിൽ പറ്റും. ലാപ്ലേഷ്യൻ നമുക്ക് ഈവൻ 6th ഓർഡർ ഡെറിവേറ്റീവ്, എത്ര ഓർഡർ ഡെറിവേറ്റീവ് ആണെങ്കിലും നമുക്ക് ഫൈനൈറ്റ് എലമെന്റ് വെച്ച് സോൾവ് ചെയ്യാൻ പറ്റും.
ഓക്കെ ഓക്കെ. നിങ്ങൾ വിദ്യാർത്ഥികൾക്ക് ചോദ്യങ്ങൾ ചോദിക്കാം കേട്ടോ. സാർ നേരത്തെ പറഞ്ഞ പോലെ മലയാളത്തില് ചോദിച്ചാലും മതി. ഇനിയിപ്പോ നിങ്ങൾക്കാണെങ്കിൽ ഈ വിഷയമല്ല, വേറെ മാത്തമാറ്റിക്സിന്റെ എന്തെങ്കിലും റിസർച്ച് സാധ്യതകളോ അങ്ങനെ നിങ്ങൾക്ക് അറിയണമെങ്കിലും അതും ചോദിക്കാം. ടീച്ചിങ് അല്ലാതെ വേറെ എവിടെയെങ്കിലും റിസർച്ച് അസോസിയേറ്റ് ആയിട്ട് അങ്ങനെ സാധ്യത ഉണ്ടോ അങ്ങനെ എന്തെങ്കിലും നിങ്ങൾക്ക് ചോദിക്കാണ്ടെങ്കിൽ ചോദിക്കാം.
Chat box question. Sir, say about your research in FEM. My research in FEM. So what we try to do, so maybe I can stop share for a moment and show you some slides. പറയാം 3D പറയാം. I did not want to go to my hold for a moment. Let me dig where are the slides. Okay. Okay, one moment. Let me just find difference. Let me share again. One more questions. I don't think I can share. Okay, I can share. Sorry. So what we are trying to I was trying to do in my research was we are trying to model tumor growth in 2D. Okay, so for example, this is a typical illustration depiction of tumor growing in 2 dimensions. So this blue dots are tumor cells. The red color is the interstitial fluid in which the cells are embedded. So what happens here is cells, because of the stress, they will move to the periphery, and because of the stress, it will expand. Okay? So that is called a tumor growth. Okay? So can we try to approximate? Can we predict this phenomenon using PDs? Okay, so we come up with a system which consists of an hyperbolic system, conservation law, which is of this form. Okay, so there is a temporal derivative, and there is an advection term with a source term. So that's a hyperbolic PD, and then there is an elliptic PD to model the cell velocity, and then there is an heat equation kind of equation for parabolic equation to represent the Newton conservation. Okay, you see here there is a spatial derivative, and here there is a complicated spatial derivative, and here there is an advection term. Okay, so we were trying to solve this one using finite element method. In fact, using finite element, finite difference, and finite volume method. I don't have enough time to let you know what is finite element method, but keep in mind that it's similar to finite volume. Finite element method, finite volume is using constant approximations of system, basically that. Okay, so this is a 1D model, and another model we were trying to solve is a 2D model. I will show you that. Yeah, so this is another system we are trying to solve. So here this does the same system, but it's in 2D. So we have an advection term, which is divergence now, and we have a viscosity pressure system, which is elliptic, and we have a Newton constellation system, which is parabolic. Now you see the domain, the geometry here, it's very complicated. It's not at all Cartesian. Okay, so you have to appeal to finite element method, which was the starting point of the talk. You always have to appeal to novel methods like finite element to solve complicated problems. So this is kind of my research, what I do, and then yeah. So that's it. As a 3D problem, what it means is that instead of, so now this is a 2-dimensional domain growing in time. Okay, so that means 3 dimensions, 2 space and 1. Somebody has drawn on my slide. I don't know. So maybe I can also do that. Yeah, I can annotate. Nice. So this is a 2D problem. So we have one time and we have 2 space. This is a spatial domain which is growing upward in time. Now imagine you have a ball in 3D. Okay, so it's a ball in 3D and it grows in time. So there are totally 4 dimensions. Okay, 3 space and 1 time. So this 3 spatial you will solve using FEM, and this one you will solve using FEM, which is a 3D problem. Okay, so this what we have done is an approximation to the 3D problem, which is a 2D problem. Now you can solve the full 3D problem. I mean, imagine a tumor sphere that's growing, and imagine that sphere is growing in time. Okay, so that there also we can apply that. So this is another application of finite element in 3 dimensions. But when you do finite element in 3D, you have to use quadrilateral. Sorry, you have to use what is that called? 3D analog of triangles. I forget its name. So you have shapes like this, 3D shapes like this, that fills the space. Like this. Okay. So in 1D it's interval, 2D it's triangle, and 3D you have to use triangular cylinders. So this is 1D, this is 2D, this is 3D. You have to tessellate the space using different geometries. Any more questions?
Sir, tumor growth നമ്മളിപ്പോ ഏത് ടൈപ്പ് ട്യൂമറിനും ഇത് അപ്ലൈ ചെയ്യാൻ പറ്റുമോ? ഉദാഹരണത്തിന് നമ്മള് രക്താർബുദം അങ്ങനെയുള്ള
ഇല്ല സാർ, ഇതിപ്പോ നമ്മള് സോളിഡ് ട്യൂമേഴ്സിനാണ്. ഓക്കെ, ലുക്കീമിയ മോഡലിംഗ് ഈസ് വെരി ഡിഫറെന്റ്. കാരണം അവിടെ വരുന്ന ന്യൂട്ടോണിയൻ ഫ്ലൂയിഡ് ഡൈനാമിക്സ് ആണ്. Because blood is a non-Newtonian fluid dynamics. Blood is fundamentally a non-Newtonian fluid. So there also we can use FEM, but the formulation is fundamentally different. We are currently using the solid mechanics basically. Solid mechanics plus some amount of fluid mechanics. But when we solve leukemia or flowing problems involving a flowing fluid, then we have to the change is from modeling side itself. Okay, we have to consider it as a non-Newtonian fluid, and leukemia will be a perturbation over this non-Newtonian fluid, something like that. But to answer your question, of course, we can use finite element method, right? When we after we formulate the question. My point is the formulation is different from what I did here.
Is there any questions from the part of audience? You can ask anything related to mathematics research, because Gopi sir have lot of experience in mathematical research. in India as well as in abroad. So you can ask the research facilities and opportunities in India and abroad.
I can do one thing. I can share my contacts here. So if you have any, if you want to ask any question here, please. You can. I think I sent to everyone. So, and this is 9468276. If you have feedbacks also, you can mail me. No issues. If you have research related questions, you can post me in the you can call me or you can put me in my email.
നിങ്ങളുടെ ഫീഡ്ബാക്ക് ഫോം ചാറ്റ് ബോക്സിൽ ഇട്ടിട്ടുണ്ട്, നിങ്ങൾക്ക് ഫിൽ ചെയ്യാവുന്നതാണ്.
The topic was a little bit advanced, but I kept it like that way because you should be knowing what's happening outside. I guess it was a little bit not accessible to the BSc guys, but one suggestion I can make is you try to read what are vector spaces, inner product, what is linear functionals, all these things. Okay, these are topics that you can usually learn a little bit by yourself. At least you can appreciate what's going on. Okay? So BSc students, even though it's an MSc topic, try to read topics outside your parallel. It will help in your BSc curriculum also. If you have any access nowadays, because thanks to the pandemic, most of the books are available online for free. So you can Google and you can find whatever you need. So make advantage of those things. So from my talk, what I can suggest is you try to Google what are inner product vector spaces, all these things, and try to get a feel of it.
Gopi sir, can you share the research experience at Australia and any comparison with India and Australia?
That's a very difficult question. That's a very, very difficult question. Fundamentally, I don't want to compare India with any other country. It's often said basically. But I can tell you about the experience in Australia. It was very pleasurable, peaceful. The research culture is a little bit different, and the whole postgraduate education culture is a little bit different from India, which is it's a little bit supervisor oriented in India. In London also, in UK also, it's a little bit supervisor oriented. But abroad, in Australia and other European countries, it's more student oriented. I mean, you can present a problem, you can solve, and you can publish on. The supervisor will give you, eventual occasional feedback. So that is my experience. So I was more enjoying Australia. But now I don't think there is not much point of talking about experience in Australia, because or any other country as of now, all these borders are closed, especially to southern countries like Australia and all. They are not admitting anybody to. So even if we get an admission to PhD in other countries, possibly have to work from home, which does not make it doesn't make too much sense to me, because the work at Australia is different from India to Australia. But if things are getting cleared, eventually it will. It's a very promising nation. It's a very peaceful nation, except December it's very hot. Otherwise, it's very pleasurable. The work culture is really captivating. So you can keep that as an option for postgraduate education. Undergraduate education, I will mostly recommend India because it's cheap and it's better than other countries. It's a very broad question. If you have very specific questions, you can email me. I can give a reply.
Okay, sir. ഞാൻ കുട്ടികൾക്കൊരു മോട്ടിവേഷൻ ആയിക്കോട്ടെ എന്ന് കരുതി ചോദിച്ചാണ്. കാരണം പലരും ഡിഗ്രി കഴിഞ്ഞിട്ട് പുറത്തേക്ക് ഈ MSc ചെയ്യാനുള്ള സാധ്യതയെ പറ്റി ചോദിക്കാറുണ്ടേ. അപ്പൊ അത് എങ്ങനെയാണ് എന്ന് അറിയാൻ വേണ്ടി ചോദിച്ചാണ്.
Instead of trying to go abroad, try to get a degree, try to do your MSc in IITs or IIS or some kind of prestigious institutes in India itself, because master students won't get a handsome scholarship abroad. Otherwise, you have to apply for some extra scholarship and. So what I will suggest is try to focus on our own institutes, which will be much cheaper and you'll get a better education. PhD or higher postgraduate studies, maybe it's always better to consider abroad, because you'll get that global exposure.
Okay, sir.
Yeah.
സാറേ ഇനി വേറെ ചോദ്യങ്ങൾ ആർക്കും ഇല്ലാന്ന് എനിക്ക് തോന്നുന്നു.
ശരി
നമുക്ക് വൈൻഡ് അപ്പ് ചെയ്യാം സാറേ.
ഓക്കെ.
Jyotika Suvash, please take charge.
Yes, sir. Thank you so much, Gopikrishnan sir, for your very precious time, as well as for your very information. Sir took sincere effort in explaining about finite element method in one dimension. Again, thanking you very much, sir, for your immense guidance and for making this day a fruitful one. Now we have reached the concluding part of the function. Our program is incomplete if we forget to mention all of them who have helped us a lot in making this function a successful one. For the vote of thanks, I call upon Ms. Priya Philip, Assistant Professor of Mathematics and Statistics Department. Ma'am, please.
Okay. Good afternoon, all of you. On behalf of Department of Mathematics, St. Stephen's College, Uzhavoor, I, Priya Philip, would like to thank our principal, Professor Lalli K. Siriyak, for her strong motivation and support in organizing this webinar. I express my sincere gratitude to our bursar, Reverend Father Jeans Nellikatil, for his support in organizing this webinar. I would like to thank our keynote speaker, Dr. Gopikrishnan Sia, Doctor Research Fellow, IIT Mumbai, for such a wonderful and informative sessions on finite element method in one dimension. I am grateful to all teachers from other colleges, research scholars, and students for participated in such a webinar. Lastly, I would like to thank our head of the department, Lieutenant Jace Kurian, and the Saviezza team coordinator, Assistant Professor Tina Jose, for organizing such a informative webinar. Thank you.
Okay, thank you. Thank you once again, Gopi sir and other teachers.
Thank you very much.
Thank you, sir. Feedback form fill ചെയ്തിട്ട് exit ആവുക. Okay.